Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this presentation is about the pressurization system on the Boeing 737. So we'll be covering the pressurization system on all models of the 737 from originals through to the MAX. Pneumatics and air conditioning are not covered here. I know the FCOMs roll these all into one under air systems, but I've broken them out into these three subjects of pneumatics, air conditioning, and pressurization. Pneumatics and aircon are covered in separate presentations. If you haven't seen the other two presentations, I would recommend that you watch those first, but it's not essential. And finally, always treat your company training and manuals as the authoritative source of information. So, by way of overview, the aircraft is pressurized by bleed air supplied to the packs and controlled, or the airflow controlled by outflow valves. So that's the big picture. Question: are the cargo holds pressurized? This is quite a common question that you come across on line training or on the line. They are sealed and pressurized, but they're not air conditioned per se. They're actually heated indirectly, but they're not air conditioned per se. That's covered in the air conditioning presentation. So there are two pressure equalization valves in the aft bulkhead of each cargo compartment, and you can see I've indicated it there in the red circle. The valves let only enough air into or out of the cargo compartments to keep the pressures almost the same as cabin pressure, so that the holes don't collapse or explode. So it kind of begs the question: why have the valves? Why not just let the air flow freely into and out of the hold? Well, the answer is that they're there to isolate the holds from the air conditioning system for fire protection. So it's actually a regulatory requirement that the air doesn't mix to give the hold its fire rating. The cargo compartments also have blowout panels in the ceiling and the bulkheads, and these are there to provide pressure relief at a greater rate than the pressure equalization valves in the case of a rapid depressurization. Next question: is the E&E bay pressurized? Answer: yes, it is. Everywhere within the fuselage, between the forward and aft pressure bulkheads, with the exception of the two wheel wells, are pressurized. This includes the cargo holds and the E&E bay. The pressurization schedule, it's designed to meet FAR requirements as well as maximize cabin structure service life, and it's a compromise between basically cabin air quality and not putting too much stress on the structure of the airframe. The pressurization system for the 737 uses a variable cabin pressure diff schedule based on the aircraft cruise altitude to meet these design requirements. And in this respect, it's actually quite different to most other airliners. Most other airliners have a gradual pressurization schedule or a constant. With the 737, it's in these four distinct bands, which is everything up to 18,500 feet. It schedules to the landing field elevation, or the delta P is landing field elevation. Between 18.5 and 28, it goes to 7.45 psi. 28 to 37, it goes to 7.8 psi, and above 37, 8.35 psi. You can see the two photos on the right that I've taken. The one on the left was taken at actually passing flight level 300, but to go to a cruise altitude of from memory 320. So you can see that the delta P there is 7.8 psi. as per the schedule. The photo on the right was at a steady flight level 400, so we've got a delta P of 8.35 psi. There is a facility or an optional reduced cabin altitude system. The standard pressurization system ensures the cabin altitude doesn't go above around about 8,000 feet in normal operation, but in 2005 this reduced cabin altitude system was certified, and with this the cabin altitude will only reach a maximum of 6,500 feet. Obviously, to accommodate this, the delta P has to be increased, and you can see on the schedule that two of the delta P's have actually increased. The 28 to 37 is now up to 8.44, and above 37 it's 8.99. The payback for this higher delta P is a 20% reduction in the airframe life cycles. So it's down from the standard 75,000 to reduced to 60,000. This option is almost exclusively taken by BBJ customers who, now there's two issues with this. One is that BBJs do a fraction of the cycles of airline operated 737s, so the lifetime limit will never be reached in BBJ operation. But I guess the other thing is that the passengers on the BBJ, because they can do much longer flights, want to arrive there in feeling as fresh as possible, and that that high delta P, the lower cabin altitude, helps facilitate that. The normal in auto mode schedule cabin rate of climb and descent is actually set by the airline, or at least their maintenance department. It's a customer option, and it's a dip switch setting what you go for. The rate of climb options are either 600 or 750 sea level feet per minute, and the rate of descents are either 350, 500 or 750 sea level feet per minute. Most airlines tend to go for the higher figures. You can see in the photograph we've got one which, allowing for parallax error on that, is probably 600 feet per minute, which is fairly standard. On the descent ones, if you go for the lower rate of descent, that will actually bring forward your top of descent. So obviously there's a cost implication with that, leaving cruise altitude earlier. These two boxes I've highlighted in the photograph in the E&E bay, they are the cabin pressure controllers, and on DCPCS, digital cabin pressure control system aircraft, there are two of them, and that's them that you see in the photo. The active controller alternates every flight, so only one of those is active on any particular flight, assuming normal operation. If the active controller fails, then the alternate one automatically kicks in and takes over. On pre-digital cabin pressure control system aircraft, which is pre-October 94, those aircraft have only got one cabin pressurization controller. This is a close-up of those cabin pressure controllers. To correctly determine the flight phase, each cabin pressure controller gets its air data, and the particular parameters it gets are static pressure, altitude, uncorrected altitude, and barocorrected airspeed inputs from both ADIRUs, which I guess might come as a surprise to some people where these inputs come from. But those three parameters come from the ADIRUs. It actually also gets engine N1 and N2 data from both SMIDs, the store management yaw damper computers, and ground logic from the PSEU. All of those data inputs are to, as I say, correctly determine the flight phase. Now each cabin pressure controller actually measures the actual cabin pressure at the sense port on the front of the unit. Now they're in those gold circles, and this, I guess, is further proof to my opening question to you at the start of the presentation, whether the E&E bay is pressurized. Well, yes it is, and yes it must be, because that's where the CPCs actually get their cabin pressure data from. If the cabin pressure sensed by the active cabin pressure controller is different to the scheduled cabin pressure, then the CPC sends a signal to adjust the outflow valve accordingly. Okay, the auto fail light. If the auto system fails, the auto fail light will illuminate, but it will actually remain illuminated even though the alternate system has kicked in. The way you get the auto fail light to extinguish is to move the mode selector to alternate. Now this is just tidying up really. It's not actually necessary because the alternate system, as I say, does kick in automatically, but it will get rid of that annoying light. The off-schedule descent light. So if you do have to return to your departure airfield, you don't need to make any adjustments whatsoever to the pressurization panel. The off-schedule descent light will illuminate. Don't worry about it. That's normal operation. But the controller will program the cabin to land at the takeoff field elevation. So it's all automatic. The standby mode, now this is only installed on the CPCS aircraft, so these are the pre-October 94 aircraft, which have only one pressure controller. So if the auto controller fails, then you manually go across to the standby system, and you just set the desired cabin altitude in that window for your particular flight level, and you read it off the decal below. So you can see, just taking at random, a figure off there. If you want to fly at say 32,000 feet, you read across on the decal and you see you need 6,000 feet cabin altitude to be set in there. Now I've got a figure in there of 13,990, which is the maximum, and I was doing that on an air test to raise the cabin to 14,000 feet to check the operation of the PSUs. You would never normally have it set that high, and that also explains the cabin altitude and the cabin VSI that you see over on the left. The cabin rate adjuster, rate selector, adjusts the cabin rate of change of altitude between 50 and 2,000 feet per minute. The index is probably where you want to have it set to, and that's about 300 feet per minute. But you can see how, for whatever reason, I was we'd obviously acclimatized to the high rate of climb, and although we wouldn't have started off with it that high, we've increased the cabin climb just to get things moving on the air test. Manual mode. So this is available in both DCP and CPCS aircraft, and in this mode you're driving the outflow valve directly. Now it can be confusing when you're new on type, you know, when you come across this first in the sim, which way to move the close open, you know, what that actually does to your cabin air. A wizened old TRE gave me the top tip many moons ago that the sense of that switch can be remembered by moving the switch toward the center of the aircraft, i.e. to the left, keeps the air inside the aircraft. Moving the switch to the outside of the aircraft moves the air outside. So I'll offer you that for what it's worth. Again, you can see with the numbers in the window, I was operating this on an air test to get the cabin altitude up to 10,000 feet to check the operation of the cabin altitude warning horn. And here is the cabin altitude warning horn. This will sound whenever the cabin altitude exceeds 10,000 feet. It's an intermittent horn, and it sounds like, because it is the same oral warning unit generating the sound, so it is the exact same sound as the takeoff config warning horn. Top tip for you, if you get this in either real life or in the simulator, don't forget you've got an altitude horn cutout button just up there. So if this goes, once you guys have both noted and acknowledged the fact that it's going, then you can stop that horn and help hear yourself think and concentrate on the task in hand. The passenger oxygen masks don't drop until 14,000 feet cabin altitude. So you get the cabin altitude warning horn at 10,000, but the oxy masks don't drop till 14,000, although you can obviously release them manually at any time. Now, following the Helios accident in 2005, where the crew misidentified the cabin altitude warning horn as the takeoff config warning horn, these two new red warning lights were fitted, saying cabin altitude and takeoff config, just to spell it out to crew which was which, and they've been mandatory ever since. Okay, so let's have a look at pack failures now. If you dispatch with one pack in op, then from the MEL your maximum altitude is flight level 250. Now if a pack fails when above this level, then what do you do? Now this is really, I guess, between you, your company SOPs and your training department, but I would say that you should at least consider descending down to flight level 250. Now Boeing don't mandate what you do either way. You can stay at 350 or whatever you're at. The packs will cope, but obviously you've got to consider what would happen if the other pack were to fail. Now if the other pack were to fail, then the cabin altitude will climb. Now the photograph I'm showing you on the right, again, was a photograph I took on an air test where took the aircraft up to 35,000 feet and deliberately, I say under test conditions, switch both packs off. And this is to check the integrity of the seals on the aircraft. A new aircraft, the cabin should climb with a no higher rate than 2,000 feet per minute. This particular aircraft, you can see, was climbing at about smidge over 3,000 feet per minute. My point is in showing you this, that it's not an uncontrollable, or it's not a rapid depressurization, I should say. It's not a rapid depressurization. It's quick, and you need to do something about it. But it's not hugely dramatic. In 2013, Boeing upgraded the DCPCS panel by fitting a more reliable electronic outflow valve position indicator. This had previously been mechanical. Mechanical indicators are always statistically more likely to fail, stick, jam, whatever it might be, than electronic indicators. So that was one of the reasons for going for this. Cost was undoubtedly another, and parts obsolescence, I think, was the other reason. So the displays are now all LED. They were previously LCD. So LED again takes less power, which is less heating in that panel. And a bit of trivia for you, would you believe that the microprocessor to drive the display functions is actually housed within that integrated light plate, which I find amazing, because the light plate's only millimeters thick. It's probably about 5 mil thick, and to fit a microprocessor in there which drives the functionality of that, personally I find it incredible. But there we go, that's miniaturization for you. Smoke clearance functions. The photo there is an old 737-200 in cargo configuration, which had a smoke clearance switch. On later 737NGs, the cargo fire smoke detector actually sends a signal to the cabin pressure control system to trigger the cabin pressure to descend at 750 sea level feet per minute, and this helps prevent smoke penetration into the passenger cabin from the cargo areas. And again, this all goes back to what I say about the not letting cargo smoke mix with passenger smoke. High altitude airport operations system. This is an optional extra. For those airlines which envisage operating into airfield elevations above the basic 8,400 feet, and this allows operations up to 10,000 feet on the NG, or most NGs, or actually up to 14,500 feet on the Series 6 and 700 aircraft. So these are places like, well, La Paz springs to mind, but there are other airfields in China and around the world which need this functionality. So changes of this include the addition of a high altitude landing selector switch, which you can see there on the right hand side. The cabin altitude warning horn will now activate at 14,000 feet instead of 10,000 feet. There's an extra hour of emergency oxygen stored in the aft cargo compartment. Takeoff thrust should be extended to 10 minutes, or 10 minutes takeoff thrust will be available in the engine out case. Winglets are mandatory and carbon brakes are recommended. Obviously that's because the true airspeed is so much higher on landing. You're up against brake energy limits. These are the various pressurization valves on the 737. The big one there is the main outflow valve. Above and below it you've got positive relief valves, and the negative relief valve is over there up on the top right of the picture. So in order then, the outflow valve. This is, of all of those valves I showed you on the previous photograph, this is the only one actually controlled by the pressurization system. And it regulates the cabin pressure by adjusting the outflow of cabin air. So in plain English, it opens and closes as needed to maintain the pressurization inside the aircraft. The outflow valve has actually got no less than three motors. One auto mode motor from each cabin pressure controller, and another one from the manual mode motor. So you can see that this is a DC-PCS aircraft because it's got two auto mode motors there. And then hiding just out of view is a smaller manual mode motor. So three motors. That's a good level of redundancy. Now, as a further fail-safe, there are actually aneroid altitude switches on each auto mode motor, and these will override the cabin pressure controller signals and close the outflow valve if the cabin pressure altitude reaches 14,500 feet. You can see them, those sort of conical shapes on the top of those motors are those aneroid switches. Now, those aneroid switches do not affect the manual mode operation of the outflow valve. So if you switch your control panel to manual, then that disables these, and you've got full control of the outflow valve yourself. The design of the outflow valve, the physical valve, has changed over the years. The original ones opened into the fuselage like this. Later ones opened out from the fuselage. And the final ones from December 2003 onwards, they do open out, but they were given this serrated edge to reduce aerodynamic noise. For those of you who've seen my max differences presentation, you will recognise the same or similar serrations on the aft cowling of the LEAP engines, and it's the same thing. It just helps the mixing of the airflows, which reduces noise. There are two positive relief valves, or safety relief valves as they're sometimes called, and as you saw in the original photo, they're located above and below the main outflow valve, and they protect the aircraft structure against an overpressure condition if the outflow valve fails closed. Now, these are independent mechanical devices. Let me just say that again. They're independent mechanical devices. There are no electronics or interfaces with any other components or systems. It's just a mechanical valve. The early originals, the ones where the aircraft had the service ceiling of was it 330, they are set for 8.5 psi. Later ones where they had 35,000 feet, the service ceiling, are 8.65 psi. The classics 8.65, and the NG and the Max are 9.1 psi. Again, this is something we check the functionality of on air tests. The negative relief valve, this is simply a spring-loaded panel. I mean, I think of this as like a letterbox in a house. It's very very similar. That spring is calibrated to 1 psi. So this panel will open when the pressure outside the aircraft is 1 psi more than the pressure inside the aircraft, a negative pressure situation. The only likely time this would ever operate would be in an emergency descent, i.e. when you're descending so fast you actually catch the cabin and exceed what the automatic pressure system can do. And once again, this is an independent mechanical device. It doesn't interface with anything. There's no fancy electronics. If you look at the back of this, it's simply a spring. Simple but effective. That's it for pressurization, a relatively short presentation by recent standards, but it does help breaking the systems out into these three subject areas, I feel. As ever, if you've enjoyed this video, found it useful, please do like it and subscribe to my channel. The address is given below. Liking the video helps give it prominence within YouTube, which helps get views. So thanks again for your attention, and enjoy the 737.